QuickSort is an example for divide and conquer technique. Here, first element is considered as the pivot element. The idea is to place this pivot element in the appropriate position. So for that, you are required to rearrange the elements of the array in such a way that all the elements less than or equal to pivot should be on left of P and remaining should be on the right of the P. So with that, you'll be getting two subarrays. You are required to sort that recursively. So when there is only one element, then there is no need to sort it. Now here, array indices are L and R here. Initially, when you are calling for the first time, L equal to 0 and R equal to n minus 1. When you are required to call this, whenever L is less than R, that means 2 or more elements, then you are required to call this QuickSort algorithm. So first, you are required to find the split position. Yes. So call this algorithm partition in order to find the split position and assign it to S. Then you'll be getting two sublists, one with L to S minus 1 elements and the second with S plus 1 to R elements. Call this QuickSort algorithm separately for this first subarray with indices L to S minus 1 and second subarray with indices S plus 1 to R. Now we'll see how this partition algorithm will work. So now I and J are used as the indices here. To scan from left to right, I is used, and to scan from right to left, J is used. So keep incrementing the I value till you find the element greater than the pivot element, and keep on decrement the index J value. When you find a element less than pivot, then stop there and swap these two elements. The idea here is to move the element less than pivot towards left and greater than pivot towards right. So this is to be done till array indices crosses over, that is I greater than J or I equal to J. So with that, all the elements which are less than pivot will move towards left and all the elements greater than or equal to pivot will move towards right. Now swap the jth element with the pivot element. We'll see the partition algorithm. Here P is AL, the first element is the pivot element. Set index I to L and J to R plus 1. Now keep scanning from left to right, that is keep incrementing the I value until you find the element greater than or equal to pivot, and decrement the J value till you get the element less than the pivot element. Then swap the ith element with the jth element. So this is to be repeated until I greater than or equal to J. In repeat until loop, this loop will be repeated till the condition is false. Once the condition is true, it will come out of the loop. So when this will come out of the loop, when I is greater than or equal to J, the control will come out of the loop, and then whatever swap is done when I is greater than or equal to J, you are required to undo that swap. So for that, swap AI and AJ, and finally swap the first element, that is pivot element, with the jth element. Return J as the partitioning position. Now this is the example taken to trace here. So scan from left to right. Here you are finding element greater than pivot here and less than pivot. So swap these two, again increment here and decrement these two, swap, and then here. Now you are finding the partitioning position here exactly. Now swap the pivot element with the jth element. Now we'll be getting the partitioning position at 4. So with that, look at here. When you call for the first time, L equal to 0 and R equal to 7 and partitioning position is 4. With that, you will be getting 2 sublists with size L equal to 0 and R equal to 3, and second sublist with L equal to 5 and R equal to 7. So continue this recursive tree call to sort the array elements. Now in QuickSort you have 3 cases. Best case occurs whenever split is going to happen exactly in the middle of the array. So that means the number of comparisons required in order to sort the array containing n elements, you need to find how many number of comparisons is being made with the arrays of size n by 2. Like that you have 2 sublists, plus in order to find the partitioning position you are required to do n comparison. So this is when n is greater than 1. When n equal to 1, no comparison is being made. So solve this reconciliation to find the number of comparisons. Or otherwise, you already know that the general reconciliation for divide and conquer. For that you can apply master theorem also. Here a equal to 2, b equal to 2 and d equal to 1. So a equal to b power d, b power 1 holds. So number of comparisons belongs to theta of n log n to base 2. And example is also taken in best case. This is the best case example. Solve it by yourself. Then in QuickSort we'll see how the worst case will work. So whenever the elements are already in the ascending order, if you give the input in ascending order, then this is the example for worst case. So 2, 3, 4, 5, 6, 7, 8, 9, 10 is being taken here. So scan from left to right, that is increment I. Here you are finding an element greater than pivot, and scan from right to left. Here you are finding an element less than or equal to the pivot element here. So in order to find this, you have done here one comparison. From right to left, totally 9 comparison. Look at here. So 9 comparisons. So totally 10 comparisons in order to find the partitioning position at 2. Now in the first place the partition is going to happen. Now we will be getting the smaller sublist which is containing these elements, that is 3, 4, 5, 6, 7, 8, 9, 10. So here there are 8 elements. Again, to find the partitioning position at 3, you will be doing 9 comparisons. Now with that you will be getting again these elements as the elements in the subarray. So now here partition is going to happen exactly here. So like that you will be left with 2 elements. So when there is 2 elements, look at here, I will be set to this one comparison, and scan from right to left. Here 2 comparisons. Here you are finding an element less than or equal to pivot in this position only. So totally 3 comparisons. So 10 plus 9 plus so on up to plus 3. So these are the number of comparisons required in worst case. In general, if there are n elements in the array, to find the partitioning position at the first, which will happen in the first position with n plus 1 comparison. Now you will be left with n minus 1 elements. So number of comparisons is n. So where the partition is going to happen again at the first position. So like that you will be left with 2 elements finally. Now 3 comparisons is being made. So totally n plus 1 plus n plus so on up to 3 comparisons. this can be rewritten as like this: 3 plus 2 plus 1 minus 3. So this is sum of natural number up to n plus 1 term. So n plus 1 into n plus 2 divided by 2 minus 3. This belongs to theta of n square. Now we'll see in the average case how this is going to work here. So in average case, the number of comparison required is C average of n. That we'll discuss with this example here. Look at here. The number of key comparisons made by QuickSort in an array containing n elements, so is C average of n. The partition can happen anywhere between 0 to n minus 1. In order to find the partitioning position, you are required to make n plus 1 comparisons. So after this partition, we will be left with two subarrays, left subarray containing s elements and right subarray containing n minus 1 minus s elements respectively. Now, assuming that the partition split can happen in each position s with the same probability 1 by n, we get the following recurrence relation here. C average of n equal to 1 by n summation s equal to 0 to n minus 1. Number of comparisons required in order to find the partitioning position is n plus 1. With that, you will be getting two subarrays. The first subarray containing s elements and the second subarray containing n minus 1 minus s elements. So this is when n is greater than 1, and when n equal to 0, no comparisons, and when n equal to 1, there is no requirement to do the comparison at all. So when you solve this recurrence relation, the final answer what you are going to get is this. Look at here. So this average case example is illustrated with this example. Now here there are 10 elements here. So split can happen anywhere from 0 to 10. So now with equal probability 1 by n. In order to find the partitioning position, n plus 1 comparisons is being made. Okay. So then you will be getting two subarrays with s elements. Look at here, in the first subarray, split is happened at this index, that is 3. Now the first subarray contains 3 elements and the second 6 elements. How do you get that? N minus 1. Number of elements in the array is 10 here. So 10 minus 1 is 9, 9 minus 3 is 6. So n minus 1 minus s. So sum these split positions. So in average case, the number of comparisons is equal to 1 by n summation s equal to 0 to n minus 1, because split can happen anywhere in the array from 0 to n minus 1 with equal probability 1 by n. The number of comparisons required to find the partitioning position is n plus 1. With that, you will be getting two subarrays. Once you find the partitioning position s, so you will be getting two subarrays. The first subarray containing s elements and the second subarray contains n minus 1 minus s elements. Thank you.